Hello, this is MATH1131 calculus, and we're going to have a look at an old sample test. This is sample test 2. This is an old test from 2008, session 1, version 8A. You can find the questions in the back of the calculus booklet. I will just summarise them here. I won't write them all up. You find the exact wording in the booklet there. And we'll go through and solve these, and please to pay particular attention to setting out and try and, when you're doing your own solutions, try and model the setting out on the solutions that you get from your tutor and from what you see here as well. So we're going to be, the first question says we're given this function which is a cubic, x cubed minus 2x squared minus 3x plus 3, and we're asked to show that it has a 0 on each of these two intervals between 0 and 1 and 2 and 3. So this is going to be an application of the intermediate value theorem. Now, again, you must write down carefully what the conditions are for the intermediate value theorem. So first thing to note is that my f is continuous everywhere. It's a polynomial. This is a polynomial. All polynomials are continuous everywhere. And so this is continuous. But you must write that fact down because I need, that's one of the conditions for the intermediate value theorem. So f is continuous everywhere. Now, to show it's got a 0 in this interval, I just have to show that when I evaluate f at each of these 2 points, I get a change of sign. So I have to cross the axis somewhere in the middle. So I'll work out f of 0, and that's easy, that's 3, which is positive. And I work out f of 1, we expect that to be negative. So if I work out f of 1, I'm going to get minus 1, which is negative. So I'll get 1 minus 2 minus 3 plus 3. So I end up with minus 1, which is negative. And therefore, by the intermediate value theorem, by IVT, you can abbreviate it as IVT. That's important, the fact that I've mentioned it's continuous. So by the intermediate value theorem, f has at least 1, so I should say here at least 1, 0 in the interval between 0 and 1. And I can put round brackets here because we saw that neither of these was 0. In fact, it's got exactly 1, but the theorem says it must have at least 1. And I do a similar thing for the next interval. So, and f of 2 equals, and f of 3 equals, I've got to show there's a change of sign. So I put 2 in, I get 2 cubed minus 2 cubed, that cancels. So I get minus 6 plus 3 is minus 3, which is negative. And if I put in 3, well, I get 27 minus 3 squareds, 9 twos are 18. And then I get minus 9 plus 3, and that comes out to be 3, which is positive. And therefore, again, we can say by the intermediate value theorem, f has a 0 in the interval between 2 and 3. And that's all that's required for that first question. It's worth 2 marks. I suppose 1 mark for applying the intermediate value theorem properly, and 1 mark for getting all the details right and checking that it's continuous and so on. So for question 2, we're given the function f of x is minus 2x squared plus x, and we're asked to find the derivative f dashed of x, but from first principles. Well, we know what the answer is. We can differentiate this in our heads. It's minus 4x plus 1, but we have to do this from first principles. So we need to go back to our first principles limit. And so we're looking at the limit then of f of x plus h minus f of x divided by h, and we're taking a limit as h goes to 0. Graphically, we're taking a chord connecting two points x and x plus h, and their images up on the function, and we're bending that chord back to be a tangent by taking a limit. So all we need to do then is to substitute into the first principles formula. So where I see x, I copy x plus h. So where I see x, I copy x plus h, and I've got to subtract off the function, so that will be plus 2x squared minus x, all divided by h. Now you can't just put h to be 0 in, because obviously you're going to get 0 over 0, top and bottom. So I'm going to simplify the top of this by expanding out. So expand the terms out, I'll get minus 2, I'll get x squared plus 2xh plus h squared plus x plus h, and then plus 2x squared and then minus x, all divided by h. Now if I then do a little bit more simplification on this as h goes to 0, then I'm going to get a minus 2x squared there, which will cancel with the plus 2x squared there. I'm going to get a minus 4xh, which won't simplify with anything. I'm going to get a minus 2h squared. And remember that I'm going to get a plus x plus h. The plus x will cancel with the minus x, and the h will just sit on the end. So just check I've got all the terms. Minus 2x squared cancels with that one, so that's gone. Minus 4xh, I've got that term here. Minus 2h squared, got that term there. The x's cancel and I get a plus h. So, and this is all divided by h. So equals the limit. Now I can factor an h out of the top and cancel it with the h in the bottom. And now finally, as I let x go to 0, this middle term will disappear and I'll get minus 4x plus 1. And of course, that's what we were expecting by differentiating the original function using our basic rules of calculus. So that's the end of question 2. For the third question, this is a rates of change type question. And in this question, we're given a rectangle. Again, I won't write it all up. I'll just summarise it as we go. So we have a rectangle, and it's got a length h. And we're given that the length is decreasing at a rate of 2 centimetres per second. So the length is decreasing at a rate of 2 centimetres per second. So that length is getting smaller in my rectangle, and we have a width which is increasing. So W is increasing at a rate of 4 centimetres per second. So the width, this is getting smaller, the width is getting bigger, and we're asked to find the rate of change of the area. So find the rate of change of the area when L is equal. We're given the values of L and W. L is 13 centimetres and W is 10 centimetres. Okay, so we've got a word problem, a physical problem here, and we have to calculate the rate of change of the area. So I'm going to interpret all of these words now in symbols. So if L is decreasing at a rate of 2 centimetres per second, that means the rate of change of L with respect to time is 2. I'm going to take increasing as positive and decreasing as negative. So this will be minus 2 centimetres per second, and the W dt, the rate of change of the width. Now I took increasing as positive, so this will be plus 4. And we want to calculate the rate of change of the area. Well, I can easily write down what the area formula of a rectangle is. We did that back in primary school. So the area is equal to the length times the width, L times W. And I want to find the rate of change of the area. So I want to differentiate this through with respect to t. So I want to find the rate of change of the area. So I want to differentiate this with respect to t. Now remember that this L and this W are changing, and they're both functions of t. So when I go to differentiate this, I'm going to need to use the product rule. I've got a product of two functions, each functions of t. So product rule says copy the first, differentiate the second, plus copy the second, differentiate the first. So I just use the product rule. Now it's simply a matter of substituting in the various values. So L was 13, dW dt we saw was 4, W was 10, and dL dt was minus 2. So this gives me 42, sorry, no it doesn't, this gives me 52 minus 20, and that gives me 32. Now 32 watt, that's going to be centimetres squared per second. So that means as this is shrinking this way but extending that way, at the point when L takes the value 13 and W is 10, then this is telling me that the area actually is increasing, because this is positive, at a rate of 32 centimetres per second. And so that's the answer to question 3. So all it was really was just interpreting what the words mean and remembering I had to use a product rule when I work out the derivative for this rate. The fourth question asks us firstly to state the mean value theorem. So question 4, these are all worth 2 I think, each of these questions. So question 4 says state the mean value theorem for the first part, and then we're going to apply it in the second part of the problem, which I'll get to in a moment, but I want to state the mean value theorem. Now the mean value theorem is not just a formula, it's like in those ads on TV when they say conditions apply. And so you've got to be careful to state the conditions, otherwise you'll lose marks on this. So the conditions are, for the mean value theorem, we take a function, suppose f is continuous on a closed interval AB, and it's got to be differentiable on an open interval AB, then the theorem says there exists, or there is, a real number C, and C belongs to the interval AB, the open interval AB, such that f of b minus f of a divided by b minus a is f dashed of c. Well, that's a nice formula, but what does it mean? And it's nice, you don't have to draw a picture here to get full marks, but I always like to draw the picture to remind myself of the underlying geometry here. So we've got our function. There's our function f from a to b. It's continuous and nice and smooth and differentiable. So what this theorem says is you calculate this quantity here, and that's just the gradient of the tangent, the chord, I should say, the gradient of this chord here between f of a and f of b. So it's just giving me the rise over the run for this line here. So that's all it's doing. That's the gradient of the chord. That's what's on the left-hand side. And the theorem says that somewhere there's a tangent that is parallel. Somewhere in here there's a tangent, there's a point C, so that these two lines are parallel. So this line is the gradient of the tangent at C, and they've got to have the same gradient as the chord. So that's what the theorem really is about geometrically. As I say, you don't need to draw the picture to get full marks, although your tutor might be impressed that you draw it. But what you do need to do is include all the conditions in the theorem. Now the second part, that's all for 1 mark apparently, so the second part now gives us the function f of x equals to x cubed minus 2x squared plus 5, and it asks us to work on the interval from 0 to 2. And it's asking us to demonstrate how the theorem works in this particular example. What that means is it's really asking us to find what this real number C is that makes the mean value theorem work. So I substitute everything in. So I have, I should I should just note here that f is continuous and differentiable everywhere. So there is a c, which I'm going to find, and it's got to be in the open interval 0, 2, such that when I work out the difference quotient here, it's got to equal the derivative evaluated at that point c. So I need f of 2 minus f of 0 over 2 minus 0 has to be f dashed of c. So I plug the numbers in. Put in 2, you get 2 cubed is 8, minus 8 is 0, plus 5 is 5. Minus f of 0, well f of 0 happens to be 5 as well. That's going to give me 0 in a moment. When I differentiate this, I get 2x squared, replace x with c, minus 4x, replace x with c. So I'm just, better put a 3 there. So I'm just differentiating this. That's 3x squared, replace x with c. This is minus 4x, replace x with c. So this is 0 here, and I can factor a c out of that. So that tells me I can write this as c into 3c minus 4 has to be 0. So the algebra now tells me that c is 0 or c is equal to 4/3. Now remember, the c has to be in this open interval. And so although the algebra gives us c equals 0 as a possible solution, it's not really the point I'm looking for. That's not going to be inside the open interval 0, 2. So in this case, I'm going to ignore that solution as an extraneous solution. The c I'm looking for is 4/3, which is about 1 1/3, and that lives inside the interval. So I'm going to take c equal to 4/3. And that means if I take that value at 4/3, that means that the gradient of the secant of this function on this interval at these 2 points will be parallel, will be the same as the gradient of the tangent at this point, 4/3. So that's the end of that question there. And finally, question 5 is a limit question, a more sophisticated limit question than you did back in some of the earlier chapters. This is x sine x on 1 minus cos x. So I'm taking x sine x on 1 minus cos x, and I'm taking a limit as x goes to 0. So those methods, those techniques you learnt back in the earlier chapters would not be easy to apply here. You can't divide by things or factor things out. This one is going to need to use some harder machinery, and that's we're going to use L'Hopital's rule. So I'm going to use here L'Hopital's rule. Which is a very useful tool. It's a wonderful tool for evaluating limits. It's extremely powerful technique. However, as we saw with the mean value theorem, conditions apply. And so you've got to check the conditions all the time. I'll show you when I finish this, I'll show you a quick example of a situation where L'Hopital's rule does not apply. It doesn't work properly because the conditions aren't met. So very important to check the conditions. Firstly, I've got to check that when I put 0 in, this has to be what is called an indeterminate form. That is, it's got to be 0 over 0 or infinity over infinity type limit. If you put in 0, well, you get 0 on the top. If you put in 0, cos of 0 is 1, so you get 0 on the bottom. Now, I don't like writing that, so I'm going to put inverted commas around it. It's not mathematics. It's, I'm just checking the conditions because 0 over 0 doesn't have any meaning in mathematics, but it indicates to the tutor that I've checked that the top and bottom are both 0, and so I can apply L'Hopital's rule. I can't write an equal sign at this stage because the second condition is that when I take the derivative of the top and the bottom separately, this will only be equal to that if that limit exists. And at the moment I don't know it does, so I'm always very strict with myself with this. I don't put the equal sign yet. I will at the end, but not yet until I check everything works properly. Now I differentiate the top and the bottom independently. There's no quotient rule going on here, you just differentiate them independently. Have to use the product rule on the top, so that will be x cos x and then plus sine x. And on the bottom, I differentiate the bottom, I'm going to get sine x. So just check what I've done there, product rule on the top and just simple differentiation on the bottom. Now the trouble is, when I put 0 in, I still get 0 there, and 0 there, so this is still 0 over 0. So I don't know that these actually equal each other at the moment. However, because it's a 0 over 0 type limit, I'm going to try using L'Hopital again. I'm going to differentiate the top and the bottom separately again and see what happens. So sometimes with L'Hopital, you have to persevere and do it a few times before it comes out. So I differentiate the first, so I copy the first, differentiate the second, and then differentiate that and copy the cos x, and differentiate cos sine x, I get cos x, divided by derivative of sine is cos. Now I look at that and say, well, does that limit finally exist? And the answer is yes, because that's 0. I'll get 1 there plus 1 gives me 2 over 1 is 2. So this limit exists. Now because this limit exists, this one will equal this one. So I can put an equal sign there. Once that limit exists, I know it equals the value of that one. So this limit now exists, it equals 2, and so I can go back and put an equal sign and I know it agrees with the line above. And so that is I can use L'Hopital's rule to get the answer out. And again, it's not obvious looking at this stage of your mathematics to see that, in fact, the limit of this does come out to be 2. Of course, in the class test, you haven't got a calculator, but you might like to check, making sure you're in radians. Take a number a little bit close to 0, try putting, say, 0.1 into here, and get your calculator to work this out. You'll find you should get very close to the number 2. So that's the end of the test, but I wanted just to show you an example of where L'Hopital's rule doesn't, where the conditions are not satisfied, and so you can't apply it. So this is just a little addendum. So note, there are limits where L'Hopital's rule does not apply. So let me just give you a quick example. If I look at the limit, say, as I'll go to infinity this time, of, let's say, 2x plus sine x over 3x minus 2 sine x. Now again, in this case, it looks all right at the beginning. As I go to infinity here, this is that's becoming very big. We don't know what this is doing, but that's becoming very big. The bottom's becoming very big. So this is of indeterminate form. It's infinity over infinity type form. So you might try using L'Hopital. So I won't put an equal sign because it in fact doesn't equal it. But I try differentiating the top. So I will get 2 plus cos x. And on the bottom, I'll get 3 minus 2 cos x. And the trouble with this limit now is if I try and let x go to infinity, well, this is 2, doesn't do anything, but the cos x just wobbles along, and if I add 2, it still wobbles along. So the top's not approaching any finite number, and neither is the bottom. So this limit does not exist. Does not exist. So that doesn't mean this doesn't have a limit, it simply means that L'Hopital's rule doesn't satisfy the requirements. It satisfied the first requirement, that it was of indeterminate form, but it didn't satisfy the second one, that this limit of the derivatives, the quotient of the derivatives, has to exist in order for this to be equal. So in this case, I need to actually go back and use the techniques that we learnt back in your first topic. So I can work out this limit, so I'll just copy it again. So that was the limit we were working out. And all I'm going to do to work out this limit, as you did back in the first topic, divide everything through by the highest power of x in the denominator, which is x. And Now, because sine is bounded, this can't be any bigger than 1. As x gets very big, this is going to 0, this is going to 0, and the answer, in fact, is 2/3. So you could work out the limit by other means, but in this case, L'Hopital's rule, the conditions don't apply. That's why it's always very important to check the conditions when you're applying L'Hopital's rule. So I think that's probably enough on sample test 2.